So we're going to start with talking about horizontal springs. And we'll look some more at vertical springs, and we will go from there. Okay. So okay. And as usual, you have to let me know if you can't see some of the writing, because I don't always see what the screen sees when I do this.
So this is horizontal springs?
Yep, horizontal springs we'll start with. We're going to work some problems today. I think I've got it where they can see it and you can see it, and I'm not cutting any words off. So what forces would be in play with a horizontal spring? What forces will be in play when we talk about horizontal springs? So we've got some sort of scenario. We're going to start with a smooth tabletop. So when we use the word smooth in physics, what does that tell us? It's frictionless. The assumption is that it is frictionless. So we're going to have so let's make this 2 kilograms, 2 kilogram mass, and spring constant will be 100 newtons per meter. Mass is 2 kilograms. So this, when we do this, this one's a little bit harder to pick out where equilibrium needs to be at first, because vertically you can see where the mass hangs down to. Like I put a mass on a spring, it hangs down to some distance, and I'm like, okay, that distance this is where equilibrium is. Gravity down, balanced by spring force up. Easy to see. And we'll do some of those today too, I think. We'll see. We may need to do those tomorrow. But what we use for our equilibrium position in this case, equilibrium position will be the unstretched length. Unstretched length of the spring. I probably could also say uncompressed, but that's kind of awkward. So it's the normal length of the spring, unstretched length. So in this case, I'm going to mark for myself where that is on this diagram. Let's go. And it doesn't really matter where you pick as long as you're consistent. So I'm going to put it right through the middle of the mass. And I'm going to call this position equals 0 meters. Put it right through the center of the mass. So that's going to be my equilibrium spot. That's where my spring is not stretched out, nor is it compressed in. I just took the spring, attached it to the wall, attached it to the block. That's it. Okay. So how would we start the spring into motion? What has to happen for us to get the spring to start oscillating? Say again?
You gotta stretch it.
You can either stretch it or you can compress it. Either way is fine. So let's come down here. Let's draw another one. So which one do you want to do? Compress or stretch? Okay, we'll do a compress. Okay. So compress would look like this. And I'm going to say this is 0.75 meters. I'm going to keep my equilibrium. It's right there. So that here to here is 0.75 meters. So let's ask, what force is required to compress the spring 75 centimeters? What force is needed to compress the spring 75 centimeters? So we're going to look at how this mathematical. No.
Teachers, please check the email that was just sent out. If you have any students on that list, please send them to the E and F hall. If you have any students that are on the list, please send them to the E and F hall.
I'm pretty sure you guys know if you're supposed to be taking the PSAP this morning, but I'll look just in case, unless you're loitering somewhere. Oh, those are all night fairs. I don't have them. And Jacob hasn't come in here, so he's absent. And Dylan hasn't come in here. Okay. Okay, got those. Sorry, everybody. Just take a second. Okay. So. All right, so back to what we're doing. So when we take these springs and we stretch them and compress them, we start with what the equation says. And the equation always on the spring force is the spring force is equal to negative K delta X. So this displacement, X always represents displacement, but the delta X in this case will be displacement from equilibrium. So displacement from equilibrium. Try to squinch that word in on the side. And so my first question is, why is there a negative sign in front of this? What would that indicate about our force that we have a negative sign in our built-in, sort of built into our equation? Say that again. It's in a negative direction. That's usually how we interpret a negative sign. It's a little more general in this case. Say again?
Are you like, so the force, are we saying the force put on the spring or the force?
The force from the spring, the force that the spring applies is negative K delta X. Well, which way have I moved my spring in this case? I have moved my spring, this would be 100 newtons per meter, and this would be 0.75 meters. Why did I put a negative in front of the 0.75? Because the displacement is to the left. The displacement is to the left. So I use a negative 0.75. But when I do that with the other negative that's sort of built into the problem, what do I get for my force on my spring? I get a positive force of 75 newtons, which indicates that when the spring is in this position, the spring force is to the right. The outside force came in and pushed the spring to the left, so the spring force will be to the right, because the spring wants to get back to its, well, it doesn't want anything. It's not a thinking object. But the spring's, its structural property is that it will go back to its normal size. So if we push the spring into the left, it's compressed. And if it has the opportunity to, it will then push back out to its normal size. So what would happen if I pulled it out to the right? So now I'd have, I would now have this kind of thing going on. There's my center. 0.75 meters here. So force due to the spring would be negative 100 newtons per meter times positive 0.75 meters and now I get 75 newtons to the left, which is what we should expect because the force from the spring should want to get the spring, should act in a way that would bring the spring back to its natural length. So if you pull a spring out, the spring force tries to pull it back to its original length. If you compress the spring in, the spring force then applies a force out to get back to its natural length. That's what we mean by an object being elastic. It wants to go back to its original shape or its original size. We do not want elastic things for bumpers on our cars. We don't want them to spring back. We do not want the fender to spring back. And that's going to be a question about momentum, and we'll talk about that a little bit later. But that would be probably the single quickest way to break somebody's neck is to put rubber bumpers on cars. Bumper cars are fun, but not for the real thing. So we'll look at that. That's also a spring force, but it acts in a little bit of an interesting way. So now if we're talking about a rubber band is not truly elastic in the sense that it always goes back to its original position. If I take a rubber band and stretch it out and let go, it will squeeze back to close to its original size and shape. But if I compress it, it usually doesn't push out. Like I don't feel a push out to go back to where it was before. But if I pull it back, I can feel a pull back together. So it's sort of a one-sided elastic situation. So when we talk about the displacement piece gets its sign, its plus or minus sign, by did we move it to the left of equilibrium or did we move it to the right of equilibrium? Whatever the outside force did to the spring will oppose that force. And as it opposes the force, that means it'll push the object in the opposite direction. So every time you compress a spring, spring force will be out. Every time you stretch a spring, spring force will be in. Okay? So far, so good? So what shape, what would we've done these before, but what would a displacement time graph look like? Position time graph look like? For one of these. Let's see, so we'll go with position because that'll be easier to deal with. Yeah.
Looks like, I guess like a sine.
Okay. Where does sine start? What's its original position?
0. Wait, no, 1.
Sine starts at 0, 0, and goes out to 1, comes back to 0, goes out to -1 on the other side. So this is not going to be a sine function. It's not going to be a sine function because if I have my spring at the equilibrium position, will it oscillate? The spring is at the equilibrium position, no force being applied on it, it's just going to sit still. So what do I have to do to get the thing to oscillate? So let's do this. If we compress the spring, it's going to start out here somewhere, in our case, -0.75. And we don't have any numbers for time, but we know it's going to, as it uncompresses, if you will, let's go back up to this picture. So it'll be here, and some moment later it will be here, and some moment later it'll be here, so forth and so on. So our distances, we're getting closer and closer to 0. Our location of our position is we get closer and closer to the original length. The original length is what we called 0. So somewhere in here, I'm going to get closer and closer to my original length, maybe right there. And then what's it going to do when it gets over past that? Why does it shoot past its original length? What's true about the forces at its natural length? Right here, what's true about its forces? They're equal, they're balanced. So guess what happens if we have balanced forces? We keep moving the same way we're moving, which means we get to equilibrium and we shoot past it. So we get increasing speed, decreasing speed. Let's see, it's about 0.75. And we're gonna speed up back to equilibrium. We're gonna slow back down. What graph is this again? This cosine, and actually this one is a negative cosine graph. And what's going to be these pieces? These two values will be your negative amplitude and your positive amplitude. All right. Negative amplitude, positive amplitude. So what happens if we stretch it first? What changes about the graph if we stretch it? The y-intercept now will start at the positive amplitude. So the graph would be flipped. How? How is it flipped? Upside down, right? So if we stretch the spring, the graph will do the exact same thing, but in the opposite direction. Still get a cosine graph either way. Okay. So now, one more piece of this, and then we'll stop for today. What about the work done to stretch the spring? What is work? What is the general statement of what work is? The general statement for work. Work is force times distance. So in the case of a spring, if you store potential energy, you get average force times displacement squared. Show you why. What is the force on a spring? Negative kx. So if I do work, it would be negative kx times x. That's where the x squared comes from. So why do I average the force? What's the important? Why do I have to average the force here? The spring force is changing. Every force we had before spring force, like if I said, what's the frictional force? And you told me it was 22 newtons. The frictional force stayed 22 newtons as long as you did whatever it was you were doing. Or if I asked Juliet, not Julia, Julia's another class. Juliet, if we ask what her weight is, which would be extremely impolite, but if we ask her what her weight is, her weight's going to be the same number fairly consistently, right? Not necessarily every day of your life. You usually gain plus or two minus, a couple pounds every day, comes and goes. But in any particular problem, if we're working with Juliet, her weight would be the same. Force due to gravity is a fixed number to a certain extent. But spring force, the further out you pull, the bigger the force. The further in you push, the bigger the force. So the force is not coming out as a same number every time. So we use the average force. That's what the 1/2 of the F is. It's the average force. Oh, you can't see that very well. Let's do this. You come over here. You come over there. And I'm not a very good window. All right, so we use the average force to kind of grasp the fact that the force is changing from place to place. Okay? And so that would be how we would do the work. And the work is going to be done on the spring when we compress it or stretch it. Work is being done by the spring when the spring undoes the motion. Okay? Now, one more thing I wanted to say about that. I'm trying to think what it is. Usually this is about, Nathan, can you think of anything else with springs we need to hit? We've done energy.
The graph of velocity.
Oh, yeah, we'll have to do that. Not today, though. Yes, we do need to do that one. And we need to write the trig function that goes with this graph, but not today. We'll hold off on that for today. Okay. Yes, the graphs are important. Thank you. Yes.
That's the work done on the spring or by the spring?
This would be the work, the potential energy would be work done on the spring. Kinetic energy would be work being done by the spring. And I wish I'd said that last year when I was teaching it this way, because it probably would have solved all those little, why do we call it this in this case and that in the other case? But these are the things that happen. Oh, the word oscillate. Let's throw this in here because this is a word AP will use. So the word oscillate is to repeat a specific path or a motion in a particular time. Yeah, I have to get period in there too. So when we do the graphs, we'll talk about the period of the oscillation. Now, yes. Thank you. This word should not, whoa, bad computer. Just want you to slide over there. This word should not be confused with the word osculate, which is to kiss. So in physics, we oscillate, we don't osculate. Also in COVID season, osculating is dangerous. So osculate is to kiss, oscillate is to swing back and forth or do a periodic motion. So there's a new ACT word for you. So we're going to stop there for today. We have a quick quiz tomorrow on being able to calculate potential energy and kinetic energy. So those two formulas and being able to do the work that goes with those. It's pretty straightforward math. It's a math quiz basically on kinetic energy, work, and potential energy. Not this part yet. I haven't done this part enough to do that yet. Okay. All right. See you guys after a little while. I'll leave the window open if you want to stay, ask questions, whatever you want to do. I'm going to go back and check on Nathan real quick. I'll be back.
Also, I learned yesterday that you are so much better than the MTSU physics.
Thanks. College teachers have never experienced any teaching really outside of college, and they don't have to be trained in teaching. They just have to be trained in their field. So I know plenty of people that are brilliant in lots of areas and can't talk their way out of a paper sack. If they were trapped in a phone booth, they wouldn't be able to explain how to get out. So that's the hazard of college teachers.
So there were two big things that I noticed when I was helping my friend. They never had force due to gravity, they had weight force.
Yeah,
And then,
which is the same thing, you ought to call them both. So.
yeah, but it was like, I have never heard it described this way before. And then he had a problem where it was a guy riding in a car, it was, why does the seat push on you and push you forward?
Yeah.
It was the force due to inertia.
Oh.
Like, no.
Oh, now that hurts me. In fact, I used to not even let my students use the word inertia, because they didn't really know what they're talking about until we've gone, deep enough for that to be a significant issue. Okay, so you feel pretty good about this kind of problem,
Yeah,
okay? And that kind of problem,
I got, this is my answer for part C,
okay,
if that's one part we didn't get to, but my problem is I have math. Can't print math.
oh, it can't close out.
For the angular,
Oh, for the angular, yeah. So this should have, so let's back up. Where did the mass come in?
whenever we were going through velocity, and kinetic energy. That way,
But if there is, oh, they don't want you to have mass in the problem. That's not one of your
Yeah.
variables that you're
Math
on.
is not one of the.
Okay, so what you're gonna do.
Then I was having to get rid of R, which we didn't have it here.
Yeah, but we had a statement with the stuff that we had,
True.
so we could just go ahead and put that back in. So what you're probably gonna have to do then is come back to here and do force of gravity will be mg and write your mass in terms of. So you take your force tension, where we had that.
We never got a force.
Oh, yeah, we were both
We just
trying, we didn't need it. But you could find it now with everything you've got. I think so. Well, we have to just rid of it, yeah. No. Okay, let's see where that would be. No, more of it.
I was wrong.
Oh, there's him, okay.
Okay, we're good.
Okay, good. Let's say, I'm trying to think of another way to get there.
Yeah, that's the problem I was having, I was like,
You can't get, well, I can imagine how you get rid of him because it is kinetic energy, so that's the sort of a difficult part of this problem.
I was like, math's kind of canceled out every year, so that would be the only math I would have.
And then all you did was you squared your velocity, right?
Oh, no, I didn't.
And then
It's gonna be squared, so it's the.
it's 1/2 of b squared, so you got your 1/2 in there, so the square root is part of that. Yeah, so you square the velocity, you just all the stuff inside the radical. Oh, the radical. What's a radical? And then the stuff inside a radical.
I would
Just like the stuff inside an integral is called the integrand.
Didn't know that either.
And this is called an argument of a function. I don't use that one very often in high school because for in math, if your function, what your function operates on is called an argument. So like a plus sign requires 2 arguments. But a cosine function only has 1 argument. We measure coefficients. It's a whole way to talk about that.
I have another question.
Uh-huh.
Because there's like a bit of is impulse a scalar or a vector?
Impulse is a vector because it's got a direction associated with it.
That's what I thought, but they were doing it as a scalar, and I was like,
Well, they can do it, you can do it as a mount and then you can just apply the direction based on the problem. So it may be depends what they're doing. Because, it comes straight from the third law. Erase this part.
go for it.
It's still too pretty to erase because it's hard to get there. So when you do impulse, it comes from the third law because the third law says that force of 1 on 2 is the same as force of 2 on 1, but without the sign. So that gives you mass times ddt equals mass 2 ddt. When you integrate that with respect to t, well, we're gonna cancel those out because they're both dt. Then we got 0 from this, so you get 1 MP times the original equals into the original, and that's what change in potential for 1 look of the course may be different. Because of the- But yeah, it's kind of weird that when you say it was a scale. It is a feature. I know.
I felt so bad because Matt hates me about so much that he dropped things to the.
Oh, yeah, no. I hate physics too, but that just mean I hated bad enough to pass it at first.
Like, he took physics twice in high school, like 2 different classes. He was like, I love this, and he went straight to college, and that was an experience. He was like,
Yeah, yeah, well, that does it, like Miss Hall, it's Livia Serrano, used to be an English teacher, fabulous English teacher, I first loved her, and she went to Kansas. And she's still trying, she got her job as an assistant principal in another school, so it had to lose her. But, she said the only reason she wasn't on that thing is because she's got one, she teaches foreign, and she didn't understand all the words, and so she was, it was so hard she couldn't do it, she had to do it math, so that happens far more often than I'd like, but what does that really mean? We don't have enough ability to stick with it and then teach it. It helps, that's really what that amounts to, but part of that is because if I was to actually go into the field in which I have a degree, I would have a 6-figure salary. Here, I'm gonna top out at a mid-5 figure. So, until teachers are valued for what they're worth, in terms of society, it's gonna be a long time. But it's like, I can't retire, I've been told I can't retire. I can't leave and I can't retire. Dr. J says, when she retires, okay, good to know. One of my former students is like, no, you can't live until my grandchildren have you. And I'm like, you better start having kids now, because, you know. But anyway,
I'm glad you said former student, not current
Yeah,
student.
yeah.
Not your current student.
Yeah,
You have kids now.
yeah, no, but like, we had one person graduate from each physics in the first education, one, in the whole city.
Like, I'm going.
I
into
think
physics now.
there's 2 right now at MTSU. But yeah, your physics can, it'll burn you out if you're not careful, because it is hard, and it is challenging, that crazy teacher.
Well, the teacher is a-
How do you get going to teach? Man, I don't know. English.
The big part of it,
So I'm not saying something to you that I haven't said right to his face.
the really big part of it is we've had a lot of, I've been in his English class every year since freshman year. It seems like every year we have a very liberal English teacher, and he's just, he wants to have students experience something other than.
Yeah, he's
liberal
really
English.
conservative.
He's like, I hated it, because like, I'll write about something and my teacher will, like,
Yeah,
he showed us, the
I
teacher will
know.
mark it off because she doesn't like the topic, and
Right.
doesn't like what he's saying, it's
Right.
like,
well, and I understand that, because he and I have a lot of conversations, and it's funny, because we're both conservative, but in different ways. Like, there are places where he's, for the church that I attend right now, he's considered kind of liberal on that. But for my church, I'm kind of conservative, and there's some other issues, that's the issue, and that's what happens. Pretty much it. Except that we should be obeying Jesus and loving people, and I don't know why the Christians become so toxic, because if people doing that, we wouldn't have that problem. But that's just me. Also, it's not my job. I got to love you, and it would be better if you did.
it's not my job to, anytime you live. it's to
Off
show
you
the
go,
right way.
have fun.
That's how I like it.
Yeah, and so we have some interesting conversations. Wow, we're down to just a few handful, and we've got all boys left except for me. I've also had 3 friends tell me that when I get a dog, I better get a girl, because boy dogs are a pain.
What else, Doris?
They really are, okay.
That's so funny. Hey, Phoenix, you got any questions?
I do. They're all on page 313.
313, I'll be there, just a second, get me there. Give me a second to look at the problems.
Okay.
Okay, which one do you want to start with?
29.
Problem or question 29? I guess if you're on 313, it's a problem, sorry. The questions were on 311, 312. Okay, so let me. All right, so number 29. So you guys that are in here, we're working on number 29 on page 313. If you haven't done those yet. So 29 says, with what minimum speed must you toss a 100-gram ball straight up to just barely hit the 10-meter high ceiling of the gymnasium if you release the ball 1.5 meters above the floor? Solve this problem using energy. So you could solve it with kinematics actually, but it's told us to solve it with energy. So the first thing I'm going to do, and the first thing I do on every physics problem I ever work, is I draw a picture. So we're going to launch it from here, which is 1.5 meters. And they tell me the ceiling is 10 meters. And so I'm launching this thing up and it's going to hit and it's going to come back down. So what I'm going to use is the idea of conservation of energy. When I launch the ball, what kind of energy do I have when I throw it up?
Kinetic.
Okay, I do have kinetic because it's moving.
Well, and potential too, because it's in the air.
And potential too because it's not on the ground. So I'm going to have an original potential energy from gravity and an original kinetic energy due to my speed of toss. And then what am I going to have when it gets to the ceiling?
Only potential.
Only potential. Because at that moment, as it's going up, right, it goes up, slows down, stops, and then starts to accelerate back down. So at the moment when it reaches the ceiling, the minimum amount of energy would mean I just barely had energy to get to the ceiling. So I changed all my energy into total potential energy. There's no kinetic because I stopped moving. So then we would have mgh original plus 1/2 mv squared equals mgh final. And usually what you need to do for AP is you need to put where you're going to call height equals 0. So I always put a height equals 0 at I put it on the ground. Okay. So our mass is, do we know our mass? No.
About
Okay.
100 grams.
So here's what's cool about that though. I don't have the mass, but what does every term have in it? Every term has mass.
Gravity.
So I can, nope, kinetic doesn't have gravity in it. Oh, it does have a mass. Okay. Well, I'm going to do this anyway because it still works. Your mass cancels out. So in fact, although you and I know this would not be true, and you guys out there would know this is not true, it doesn't matter if I throw a ball or throw an elephant because the mass cancels out. And that's kind of weird. All right, so then we have 10, 1.5. They asked me what the velocity is, so I don't know that. And then this is 10 and 10. I'll let you finish it off from there. And then with what speed does it hit the floor? This is part A. So what's going to happen on B? I still start the same way.
But it's going to end with kinetic.
And now I end up with all kinetic. Yep. I think you can handle the algebra this time from there.
Okay, thank you. I'll let you know if I have any questions.
That's cool. We got a lot of people taking the PSAT today, and we've got some sick people, and we've got some people that had to leave for impact. So I'm down to a few, but yeah, you're good. Emily, I have your AP receipt somewhere, so I'll get it to you at some point. It's just in a big pile of those. Let's see if I have any of this to pass out to you guys. Nope, that's all standard physics. Already got y'all's done. So yeah, you folks in here don't have to submit your homework online. You can just give it to me. You're still welcome to email it, but if you want it faster, you can just hand it to me. You'll get graded a lot faster that way. Yeah.
The first two of work, you know, the scripts 24 and 27.
Mhm.
Any questions from you? They all agree?
Friction. Thermal energy is friction.
Okay.
So it'll be when you hear work done by, or when you hear energy change, mechanical energy change to thermal energy, what that really means is mechanical energy friction took the energy out and turned it into heat.
Hmm.
So that's how you need to think about that.
So the energy that, so the force from friction would be the energy that creates.
The force from friction would be the force, and then the distance that the friction acts over, force of friction times that distance will give you the work done or the change in energy, the amount of energy lost to friction. So energy lost to friction is always a out of the system. If you don't conserve, you can write, you have to write it into the to the conservation of energy statement to account for it, but it's not staying in your system. The energy is leaving its heat. Okay? Good question though. Good question. So Phoenix, I don't know if you heard that, but he was asking about when you see thermal energy in a problem. Thermal energy in a problem means that your work done by friction has removed the energy from kinetic and potential and turned it into heat. Just like if I take my two hands, I've got kinetic energy in my muscle movement, but what it comes out as is energy lost to the environment as heat.
Okay.
So work done by friction is the same thing as lost to heat energy.
So for part B,
Yeah.
so you wrote down the equation, original potential energy plus, original kinetic.
Mm-hmm.
I converted that to an actual equation. So it's I did it how you said, like, it starts the same mg original plus 1/2 mv squared.
Mm-hmm.
Would I set that equal to 1/2 mv original squared?
No, the final. So when it goes up and it comes back down, now it's just above the ground, right? So our potential energy is essentially 0. So we've transferred all the original energy into kinetic.
Okay,
So
okay.
the one on the right would be 1/2 mv final squared. It'd be the ending speed right before it hits the ground.
Okay, that makes sense. Thank you.
Mm-hmm.
Okay, I think I got part B.
Okay.
What I got was the final velocity is 14.14 meters a second.
Okay. You got the answers in the book, but I'll go ahead and look that one up for you real quick. So 29, let's see, 13 meters per second and 14 meters per second. So is that what you ended up with?
Yes, ma'am.
Okay. The textbook on the answers always gives the answers in sig figs. So we don't do significant figures in AP Physics anymore. So just round it off to something that's reasonable. If you give 1 decimal place or 2, you're probably fine. Or in this case, if you round it off to nearest whole number.
Okay, that makes sense. Thank you.
Okay. And you guys in here, you're always welcome to ask for checks on your work too, because no sense in practicing it wrong. And then you'll learn how to do it really well, badly. Because I always hate when they say perfect, they say practice makes perfect. No, practice makes permanent. Perfect practice makes perfect. Yeah, yes, you may. Mhm. Yes, sir.
I was, but I was, I wanted to ask
Yeah.
about number 23.
Mhm.
It gives you the roller coaster and it gives you its final speed,
Mhm.
and then it asks for speed halfway down. Because it like starts up here.
Right.
It gives you the final speed and asks you speed.
Right. So what you know is that the speed at the very top would have to be, the amount of energy you would have at the very top would be the same amount of energy you have throughout the whole problem. So you would have, you know enough, I think on that one, yeah. You've got, so you know it would have lost half of its kinetic energy, I mean, half of its potential energy, because potential energy is directly proportional to height. So what you've really got here is half of your MGH has to equal your 1/2 mv squared. Since they both have mass, that's will cancel out, 1/2 to cancel out, and you can, oh, wait. We want to work this one backwards. We know what the ending speed is. So we want to go use the ending speed, where the ending speed would be all kinetic energy.
Mhm.
And then go back to half the energy now would be, you would have half the total at the point you're looking. So you can find the final kinetic energy, because you know it's, when it gets to the very bottom, it's just all kinetic energy. There's no potential left. So you get that number and you can take half of it and put it in equal to 1/2 mv other squared. So,
So in this case, it would be 30. That's the final speed.
right, so your final potential energy,
Equals, and then we can bring half of it back to,
no, the third is the speed.
yes.
We gotta get
Oh,
its
we gotta
kinetic
get the
energy.
Yeah.
Yeah.
But we're not gonna advance or, well, yeah, I think
But it's okay because kinetic energy on one side
Cancel out.
will cancel out with the kinetic energy on the other side, the mass will take care of itself.
So the general one is just, and is it better?
Well, on B, it would be your kinetic energy final, which you know. Half of that will be equal to your kinetic energy at the spot you're looking.
So you would have, in this case,
You would go with kinetic energy final, take 1/2 of that is equal to the kinetic energy at the point you're looking for. You have all the information, because this would be 1/2 M, and you know this is 30. This one is 1/2 M, and I don't know. So then the M's wipe, and you're left with, the other numbers. So the thing about conservation of energy is that if you know the energy anywhere, you know it everywhere. As long as there's not friction. If there's friction, friction is always removing energy from your system. So then that makes it much more difficult to deal with.
Do you know that this behind a knuckleball?
Yeah, I do. So when you throw a slider or a curveball or any pitch with spin, the seams of the baseball are slightly higher than the skin of the baseball. And in a lot of pitchers pick balls that are even a little bit raised more than that, they pick at them with their fingers to kind of get them raised. So what happens is, because like an airplane, the baseball moves through the air, and as it moves through the air, all the air around it has to pass over and around it. If it's spinning, then you have a little bit of a lift here, and it's flat on one side, then the air that goes from here to here has to go a bigger distance on this side than it goes on that side. The weird thing about this, and this is one of the first topic we teach in physics too, just about, is called Bernoulli's, is that the faster the air flows over here, the less pressure it exerts. So a curveball with a spin sideways causes the air on the inside to move faster around the seam than on the outside. So there's high pressure out here and low pressure in here, which causes the ball to move. If you do a knuckleball, the ball is not spinning, or it's spinning in a non-sort of pattern behavior. And so the air is going, kind of like when you drop a sheet of paper, it hits the air wherever it hits the air, and the air is constantly pushing it further and all that, and so you get that sort of dancing motion. So the less you can spin it, the better the knuckleball, but it's also harder to control where it's gonna go. Because just like a sheet of paper, if I drop a sheet of paper, it's gonna go where it's gonna go. After I let go of it, there's no way for me to control the motion. And so it's all about where the seams are and the air pressure that you create around it.
Thank you.
Softball, in softball, you typically throw, you throw fastball to the regular fastball. But rise pitches are done so that the ball spins and pulls the air fast underneath, fast on top. So you got slow air down here and fast air up here, which causes the ball to actually rise. And a person that does that really good, does that really well, like you could put a rope, like from the first baseline to the third baseline, about waist height, and the ball will go under the rope on the pitcher side and go over the rope on the other side, and it's really freaky looking. A high fastball is just you throw it and it goes straight up. But the rise ball, it's almost like it goes right there, and it's just weird. But change-ups fall because you spin the ball in such a way that the air pressure is lower underneath. It's the same idea as spoiler on a car. Spoiler on a car, you want to create a downforce, so you make the air go fast underneath the spoiler and make it go a little bit slower. It doesn't have to go as far on top. That causes air pressure, atmospheric air pressure matches down the back end of the car, which lets you go faster if you so desire. But if you go too fast, you do not stay in the turn. That's a topic we will cover in the next few weeks.
Have you hydroplaned in your Jeep?
Not in my Jeep, I haven't, and the X-Trail I did once or twice, and it wasn't because I was driving recklessly, it's just, it takes a quarter inch of water to lift your car off the road.
Yeah, yesterday I was leaving baseball before on Brinkley, and I didn't gas, I just stepped on the gas and I got around turn all the time, like fish tail around the back, and that could have bad if there's a car there, so.
Yeah, you always want to spin, you always want to turn your steering wheel into the slide. Which is very counterintuitive, but that gives you the friction to be able to catch back to the road. If you steer the opposite direction, it'll make the spin worse. And can cause you to overcorrect and flip you or take you to the other side of the road and off the other side of the road. So you always want to steer into a slide.
I've heard that, I just don't know, I never knew one from them.
Yeah, it's really about trying to get your tires, if you get your tires pointing the right direction, is the slide, you will get some friction because you're trying to do the same thing that cars are already doing. But yeah, the place I get it most is, I live in Victory Point down here. And coming in or out of that neighborhood, because so many cars, like at the end of school, line up there to get out, like you guys go back way and stuff. We get oil around that area, and so there's a wreck there probably once every 2 weeks.
Do we have,
And I catch it when I turn coming out or turn coming in, I'll skid.
at the end of Berkshire, like the long exit,
Yeah,
there's like, well, it's a perfectly fine, even if it's just barely raining, you can slip nowhere, like, driving up there perfectly fine, but as soon as you step on the gas, if your back tire's down, like,
yeah. It's one of those things, there's nothing you can do about it, because when it rains, the oil will rise to the top of the water because it's less dense, and so you're gonna have that slippery layer of oil there. So your coefficient of friction goes way down. Oop, Phoenix is gone now.